On April 22, 1982, workers at the Kelly mine in Butte, Montana, shut down the dewatering pumps that had operated continuously for over a century. The decision was administrative. Copper prices had declined, operational costs had risen, and the Anaconda Company determined that continued extraction was no longer economically viable. Within hours, groundwater began reclaiming the vast network of underground workings that extended beneath the Butte Hill. Within 18 months, a lake would form in the abandoned Berkeley pit that would eventually contain 50 billion gallons of water with pH levels below 3 and dissolved metal concentrations exceeding those of battery acid. The system behaved exactly as geochemistry predicted. The failure was not operational error or regulatory negligence. It was the inevitable consequence of a design philosophy that treated continuous human intervention as a permanent condition rather than a temporary state. The mine was engineered to extract copper. It was never engineered to stop. The Butte Mining District sits atop one of the most geologically complex and mineralogically rich ore bodies in North America. The deposit formed approximately 66 million years ago when magmatic fluids migrated upward through the Butte granite, depositing copper, silver, zinc, manganese, and molybdenum in a network of veins, lodes, and disseminated mineralization. The mineralogy that made Butte valuable, chalcopyrite, energite, bornite, was intimately associated with the mineralogy that would later prove catastrophic, pyrite, the iron sulfide mineral that constitutes the primary source of acid mine drainage worldwide. The same geological processes that concentrated copper also distributed pyrite throughout the ore body in concentrations sufficient to generate sulfuric acid whenever the mineral contacted air and water simultaneously. Underground mining at Butte began in the 1870s and expanded rapidly through the early 20th century. By the time the Anaconda Company consolidated operations, the district contained over 15,000 kilometers of horizontal drifts and vertical shafts, some exceeding 1 kilometer in depth. This interconnected labyrinth penetrated the water table at multiple elevations, creating a situation where natural groundwater inflow would flood the workings unless continuously removed. The volume was substantial. Approximately 5,000 gallons per minute flowed into the mine complex from the surrounding fractured bedrock aquifer. The solution was straightforward in engineering terms: centralized pump stations that collected water from the lowest levels and lifted it to the surface. The high ore mine served as the central pump station from 1901 to 1967, when operations transferred to the Kelly mine. The pumps ran continuously. They had to. Without them, mining was physically impossible. This arrangement established a design premise that would persist for decades. The mine existed in a state of managed disequilibrium. The natural condition of the system was flooded. The operational condition required continuous energy input to maintain the void space necessary for extraction. Every engineering decision, every operational procedure, every economic calculation was made within this framework. The pumps were not a contingency system activated during emergencies. They were the foundational infrastructure that made everything else possible. When engineers designed the mine, they designed it to be pumped. They did not design it to stop being pumped. The chemistry of acid mine drainage was understood long before the Berkeley pit closed. The oxidation of pyrite follows a well-characterized reaction pathway. Iron sulfide reacts with oxygen and water to produce ferrous iron, sulfate ions, and hydrogen ions, the last of these being the source of acidity. The reaction is thermodynamically favorable and kinetically accelerated by certain bacteria, particularly acidithiobacillus ferrooxidans, which catalyze the oxidation of ferrous iron to ferric iron. Ferric iron then serves as an oxidizing agent that attacks additional pyrite, even in the absence of dissolved oxygen, creating a self-sustaining cycle that can persist as long as sulfide minerals remain exposed to water. The geochemical literature documented these processes in detail. The engineering community understood that flooding a sulfide-bearing mine would initiate acid generation. What was not engineered was a response. The Berkeley pit opened in 1955 as an open-pit operation designed to extract the lower-grade porphyry copper deposit that surrounded and underlay the high-grade vein systems. Over 27 years of operation, the pit expanded to dimensions of approximately 1.3 by 1.9 kilometers in area and over 500 meters in depth. The pit walls exposed massive surface areas of sulfide-bearing rock to atmospheric oxygen rock that had previously been protected from oxidation by the overlying material. The geometry of the pit was optimized for ore extraction, not for post-closure chemistry. Benches cut into the walls maximized mining efficiency while also maximizing the surface area available for acid generation once operations ceased. The pit floor sat below the elevation of the underground workings, ensuring that any future flooding would drain toward this single point. No closure protocol existed. The engineering documentation from the operational period treats the mine as a going concern, a system that would continue operating indefinitely or until the ore was exhausted. The concept of a managed end state in which the mine would be returned to a stable condition requiring minimal ongoing intervention was not part of the design vocabulary. This was not an oversight in the sense of something forgotten. It was a reflection of the economic and regulatory environment in which the mine operated. Closure was understood as a future event that would be addressed when it occurred. The conditions that would make closure safe or catastrophic were not part of the operational calculus. The design premise of perpetual dewatering was not merely technical, it was institutional. It shaped how operators understood their work, how managers allocated resources, and how regulators assessed compliance. The assumption was so deeply embedded that it became invisible, not a choice to be questioned, but a background condition to be maintained. The institutional environment surrounding the Butte mining complex reinforced the design premise of perpetual operation through every procedural, economic, and regulatory mechanism available. The system was not merely engineered to run continuously, it was managed, incentivized, and regulated as though continuous operation was the only conceivable state. When the decision to cease pumping finally arrived, it encountered an organizational structure that had no category for what would follow. The failure to anticipate post-closure chemistry was not a failure of knowledge. It was a failure of institutional imagination, shaped by decades of procedures that treated contaminated water as a resource rather than a liability. The copper precipitation plant stands as the clearest artifact of this institutional framing. Constructed in the early 20th century near the base of the Yankee Doodle tailings dam, the facility was designed to extract economic value from the acidic water being pumped from the underground workings. The chemistry was elegant. Acidic mine water, rich in dissolved copper, was passed over bins of scrap iron, initiating a cementation reaction, in which copper ions accepted electrons from metallic iron, precipitating as elemental copper while releasing ferrous iron into solution. The reaction Cu2 plus Fe(S), Cu(S) plus Fe2, Was, thermodynamically favorable and economically profitable. Water that entered the plant as an environmental liability exited as revenue. This arrangement created a feedback loop that fundamentally shaped how operators and managers perceived mine water. Contaminated drainage was not waste to be disposed of, but feedstock to be processed. The precipitation plant generated copper that could be sold, transforming the cost of water management into a profit center. Every gallon of acidic water became an opportunity rather than a problem. This economic logic persisted through the transition from underground to open pit mining and continued after the Berkeley pit opened. Water from heap leach pads, from the Horseshoe Bend springs at the base of the tailings dam, and from the underground workings all flowed through the precipitation plant, yielding copper and reinforcing the institutional understanding that mine water was manageable through industrial processing. The regulatory environment of the period aligned with this framing. Prior to the environmental legislation of the 1970s, the Anaconda Company discharged treated mine water directly to Silver Bow Creek, the headwater stream of the Clark Fork River. Treatment consisted of lime addition to raise pH and precipitate metals, a process that reduced but did not eliminate contamination. The practice was legal, permitted, and consistent with the regulatory standards of the era. No zero-discharge mandate existed. No requirement compelled the company to contain mine water indefinitely. The regulatory framework assumed that mine water would be managed through treatment and discharge, not through perpetual containment. When operators looked at the water flowing from their pumps, they saw a material that could be processed, neutralized, and released. They did not see a liability that would persist for centuries. Training doctrine reflected these assumptions. Operators were trained to manage water flow, to maintain pump operation, to route drainage to the appropriate treatment facilities, to recover copper and neutralize acidity before discharge. The operational manuals and procedures that governed daily work addressed the mechanics of water handling in detail. They did not address the consequences of cessation. The question of what would happen if the pump stopped was not part of the training curriculum because it was not part of the operational reality. Operators understood their role as maintaining a system, not as anticipating its termination. The Horseshoe Bend springs illustrate how contamination signals were normalized within this framework. These acidic seeps emerged from the base of the tailings dam, carrying dissolved metals at concentrations that would later be recognized as hazardous. But within the operational logic of the active mine, the springs were simply another input to be routed to the precipitation plant. The copper they contained could be recovered. The acidity could be neutralized. The flow rate could be measured and managed. The springs were not interpreted as a warning of what uncontrolled drainage might look like because they were controlled, captured, processed, and incorporated into the industrial system. The same framing applied to drainage from leach pads, from the East Berkeley pit area, and from other surface sources. Each flow was a management problem with a management solution. The possibility that these flows represented a preview of unmanageable post-closure chemistry did not penetrate the institutional consciousness. The interconnection of the underground workings created additional vulnerability that was understood technically but not incorporated into closure planning. The consolidation of operations under the Anaconda Company had linked formerly independent mines into a single hydraulic system. Water that entered at the periphery of the district drained toward the central pump stations through thousands of kilometers of horizontal drifts. This arrangement improved efficiency. A single pumping operation could dewater the entire complex, but it also meant that the failure of that single operation would flood the entire complex. There was no redundancy, no compartmentalization, no way to isolate portions of the system. The hydraulic connectivity that made centralized dewatering possible also ensured that any cessation of pumping would affect every corner of the district simultaneously. Human factors aligned with procedural and economic incentives to create an environment where closure planning was structurally discouraged. The personnel who operated the mine had career incentives tied to continued production. The managers who made resource allocation decisions were evaluated on extraction efficiency and cost control. The regulatory relationships were built around operating permits that assumed ongoing activity. No constituency within the system had responsibility for anticipating termination, and no reward structure encouraged such anticipation. The engineers who understood sulfide oxidation chemistry were not the decision-makers who determined when to stop pumping. The decision-makers who determined when to stop pumping were responding to copper prices and operating costs, not to geochemical timescales. The decision to cease pumping on April 22, 1982, was made within this institutional context. Copper prices had declined. The underground workings were largely exhausted. The Berkeley pit had closed in June 1982, and the economic rationale for continued dewatering had evaporated along with the revenue from copper extraction. From an economic perspective, the decision was straightforward. The costs of pumping exceeded the benefits. From a geochemical perspective, the decision initiated a process that could not be reversed. But the geochemical perspective was not represented in the decision-making framework. The people who made the choice understood that water would rise and that acid would form. They did not have a procedural or regulatory structure that weighted those consequences against the economic factors driving their decision. The institutional environment had created a situation where the consequences of closure were known in technical terms, but absent from operational terms. The knowledge existed. The integration of that knowledge into decision-making did not. This gap was not the result of individual failures, but of systemic design, an entire apparatus of procedures, incentives, and regulations that assumed continuous operation and provided no framework for its termination. When the pumps stopped, the operators and managers who had spent their careers maintaining the system had no protocol for what came next. The institutional imagination had reached its limit. "11 p.m. The physics of acid mine drainage operate according to principles that do not negotiate with institutional timescales or economic preferences. Once the Berkeley pit became the consolidation point for contaminated groundwater from the flooded mine complex, the system entered a phase of chemical evolution governed entirely by reaction kinetics, mass transport, and thermodynamic equilibrium. The water quality data collected over the subsequent decades constitute a detailed record of these processes, a forensic archive documenting exactly how a flooded sulfide mine transforms into a concentrated acid reservoir. The fundamental reaction driving the system is the oxidation of pyrite, the iron sulfide mineral distributed throughout the butte ore body in concentrations that reflect the geological processes of its formation. When pyrite contacts oxygen and water, it undergoes a multi-step oxidation sequence that releases ferrous iron, sulfate, and hydrogen ions into solution. The overall stoichiometry can be written as FeS2 plus 3.5O2 plus H2O, Fe2 plus 2SO, 42 plus 2 hours, though this summary obscures the mechanistic complexity of the actual process. The reaction proceeds through intermediate steps involving thiosulfate, polythionates, and elemental sulfur, each of which can follow alternative pathways depending on the chemical environment. The hydrogen ions released constitute the acidity that defines acid mine drainage. Each mole of pyrite oxidized generates 2 moles of hydrogen ions, driving pH downward with relentless stoichiometric precision. The kinetics of pyrite oxidation are slow under purely abiotic conditions, slow enough that natural sulfide deposits can persist for geological time without significant weathering. But the bacterial communities that colonize acid mine drainage environments accelerate these kinetics by orders of magnitude. Acidithiobacillus ferrooxidans and related species catalyze the oxidation of ferrous iron to ferric iron, the rate-limiting step in the overall reaction sequence. Ferric iron then serves as an electron acceptor that attacks pyrite directly, oxidizing the sulfide component even in the absence of dissolved oxygen. The products of this reaction include additional ferrous iron, which the bacteria re-oxidize to ferric iron, sustaining a catalytic cycle that can continue as long as pyrite and water remain in contact. The Berkeley pit lake chemistry prior to 2010 reflected these processes operating at massive scale. pH values consistently measured between 2.5 and 2.8 levels, at which aluminum hydroxide minerals dissolve completely, releasing aluminum ions that accumulated at concentrations exceeding 200 milligrams per liter. Dissolved iron reached concentrations of 400 to 600 milligrams per liter in the deeper water, with ferrous iron dominating due to the oxygen-depleted conditions at depth. The shallower water contained elevated ferric iron, identifiable by the characteristic red-brown color that gave the pit lake its distinctive appearance. Zinc concentrations exceeded 500 milligrams per liter, reflecting the dissolution of zinc-bearing minerals throughout the flooded workings. Copper remained above 50 milligrams per liter despite the absence of conditions favorable to its mobilization, sustained by continuous input from the underground mine pool. The mass balance of the system reveals the scale of contamination accumulation. The pit lake received groundwater inflow from the flooded underground workings, from the fractured bedrock aquifer, and from the shallow alluvial aquifer along its eastern and southern margins. Each of these sources contributed dissolved metals and acidity. The lake had no outlet, no surface discharge, no groundwater leakage sufficient to constitute meaningful export. Evaporation removed water but concentrated solutes, shifting the isotopic composition of the lake toward values characteristic of evaporated water, while increasing the concentration of non-volatile constituents. The system was a one-way accumulator, receiving contamination continuously while exporting nothing. The stratification behavior of the pit lake added complexity to its chemical evolution. During periods when surface inputs of lower-density water, particularly from the Horseshoe Bend diversions, flowed into the lake, the water column developed stable density stratification. Lighter, less concentrated water floated on denser, more concentrated deep water, creating a meromictic condition in which vertical mixing was suppressed. The chemocline separating these layers could persist for years, with the deep water accumulating ferrous iron and other reduced species, while the shallow water maintained contact with atmospheric oxygen. Periodic disruptions, landslides from the unstable pit walls, seasonal cooling that increased surface water density could overcome the stratification and trigger vertical mixing, redistributing chemical constituents throughout the water column. The landslide events documented in the pit's history illustrate the physical instability of the system. September 2010 saw a major slide on the southeast high wall, with millions of cubic yards of material entering the lake and raising the water level by approximately 1 foot. The disturbance probably triggered lake turnover, mixing deep and shallow water and redistributing the chemical gradients that had developed. Further slides in 2012 and 2013 damaged monitoring infrastructure, forced the suspension of sampling activities, and introduced ongoing safety constraints that complicated scientific access to the lake. The pit walls, excavated for mining efficiency rather than long-term stability, continue to erode and slough, adding sediment and altering lake chemistry through mechanisms that cannot be precisely controlled. The absence of natural attenuation mechanisms distinguishes the Berkeley pit from some other acid mine drainage systems. In environments where sulfate-reducing bacteria are active, dissolved sulfate can be converted to sulfide, which then precipitates dissolved metals as insoluble metal sulfides. This process can sequester contaminants in sediment, effectively removing them from the water column. Investigations of the Berkeley pit sediment, however, found no evidence of an active sulfate-reducing zone. The concentrations of dissolved copper and zinc, both toxic to most strains of sulfate-reducing bacteria, apparently inhibited the establishment of these populations. Without biological sulfate reduction, the primary mechanism for natural metal removal was unavailable. The system could not heal itself. The iron cycle dominated the lake's chemical dynamics. Ferrous iron, stable under the reducing conditions at depth, oxidized to ferric iron when exposed to dissolved oxygen in the shallow water or during mixing events. Ferric iron then precipitated as secondary minerals schwartmanite and jarosite, both iron oxyhydroxysulfates characteristic of acid mine drainage environments. These minerals formed as fine particles suspended in the water column, giving the lake its turbid appearance before settling to the bottom as sediment. The precipitation of ferric iron represented a transfer of mass from dissolved to solid phase but did not constitute removal from the system. The sediment accumulated at the bottom of the pit, available for future dissolution if conditions changed. The trajectory of the Berkeley pit lake chemistry demonstrated a fundamental principle. Acid mine drainage systems do not reach passive equilibrium on human timescales. As long as sulfide minerals remain in contact with oxygenated water, acid generation continues. As long as groundwater flows toward the lowest point in the water table, contamination accumulates. The rates may vary with temperature, bacterial activity, and hydrological conditions, but the direction of change is fixed by thermodynamics. The pit lake was not approaching a stable end state. It was evolving along a trajectory determined by reaction. The recognition that the Berkeley pit could not be passively abandoned, that some form of active intervention would be required indefinitely emerged gradually from the accumulating evidence of chemical deterioration and rising water levels. The stabilization efforts that followed were not a single coherent response, but a sequence of interventions, each addressing immediate concerns while introducing new variables into an already complex system. The history of these efforts reveals the difficulty of managing a contamination source that operates on geochemical timescales using institutional mechanisms designed for shorter horizons. The copper recovery operations that began in August 1998 represented an attempt to extract economic value from the pit lake while simultaneously addressing its chemistry. The principle was identical to the precipitation plant logic that had governed mine water management for nearly a century: pass acidic copper-rich water over scrap iron, recover copper through cementation, and return the treated water to the system. Deep pit water was pumped to the precipitation plant near the base of the tailings dam, processed through the iron beds, and discharged back to the surface of the pit lake. The operation recovered copper that could be sold, partially offsetting the costs of water management. Between August 1998 and June 2000, and again from January 2004 to February 2013, approximately 1.3 pit lake volumes were cycled through the precipitation plant. The copper recovery operations achieved their primary objective of metal extraction, but introduced consequences that would fundamentally alter the lake's physical structure. The cementation reaction that removed copper added ferrous iron to the water. Each copper ion precipitated released an iron ion into solution. The Fe-enriched effluent returned to the lake surface was denser than the water it replaced due to its elevated dissolved solids content. More significantly, the continuous pumping from depth and return to surface created vertical circulation that progressively eroded the density stratification that had characterized the lake during its meromictic phases. The chemocline separating fee-poor surface water from fee-rich deep water was systematically drawn downward as copper recovery continued. Monitoring data document this progression. The boundary between the Mixolymian and Monomolymian descended year by year until, by late 2009, it had completely disappeared. The lake transitioned from meromictic to holomictic, from permanently stratified to seasonally mixed. This transformation meant that the entire water column now participated in seasonal turnover events, with deep water rising to the surface and surface water sinking to depth during periods of thermal instability. The chemical isolation that had previously separated different zones of the lake was eliminated. The destratification had consequences that extended beyond simple mixing. When ferrous iron from the deep water reached the oxygenated surface zone, it oxidized to ferric iron and precipitated as secondary minerals. The combination of vertical mixing and atmospheric oxygen exposure triggered a massive iron precipitation event. Over 200 million kilograms of iron previously dissolved in the water column converted to solid schwarzmannite and jarosite particles that settled to the lake bottom. The visual signature of this transformation was dramatic. Sometime between February 2013 and February 2016, the lake color changed from the characteristic red-brown of ferric iron solutions to a green hue whose origin remains incompletely characterized. The iron that had defined the lake's chemistry for decades was now sediment. The Horseshoe Bend lime treatment plant, operational from November 2003, introduced a parallel intervention with its own set of consequences. The facility collected acidic drainage from the Horseshoe Bend springs, the same flows that had previously been diverted directly to the pit lake, and treated it with hydrated lime to raise pH and precipitate dissolved metals. The treatment process generated high-density sludge, a mixture of metal hydroxides and calcium sulfate that constituted the waste product of neutralization. This sludge required disposal, and the disposal site selected was the Berkeley pit itself. The decision to discharge lime treatment sludge to the pit lake reflected the same containment logic that had governed earlier surface diversions. Contaminated material should be consolidated rather than dispersed. But the sludge was not merely waste. It carried alkalinity, the hydroxide ions from the lime that had neutralized the Horseshoe Bend drainage. When the sludge entered the acidic pit lake, some of that alkalinity transferred to the lake water through partial redissolution of the precipitated solids. The pit, which had been receiving only acidic input since its formation, was now receiving a source of buffering capacity. The combined effects of copper recovery, destratification, iron precipitation, and sludge disposal produced a chemical transformation that monitoring data document with unusual clarity. Lake pH, which had remained below 3 for over 2 decades, began rising in the late 2000s. By 2015, surface pH had exceeded 3.5. By 2018, values reached 4 to 4.1 throughout the water column. The increase of more than 1 full pH unit represented a tenfold decrease in hydrogen ion activity, a substantial improvement in absolute terms, though the lake remained far more acidic than any natural surface water. The pH rise was attributed primarily to sludge alkalinity addition, though researchers noted that the expanding lake was also encountering less mineralized butte granite and alluvial gravels containing minor calcite, potentially contributing additional buffering capacity. The improvements in water chemistry came at the cost of permanent active intervention. The lime treatment plant required continuous operation, continuous lime supply, and continuous sludge disposal. The copper recovery operations, though suspended after 2013 due to landslide damage to infrastructure, had demonstrated that any future resumption would need to account for the destratification effects observed during the earlier campaigns. Every intervention that improved conditions also created dependencies. The system was not recovering toward passive stability, it was being maintained in an artificially improved state through ongoing chemical addition. The landslide events of the 2012 to 2013 period introduced safety constraints that complicated all subsequent management activities. The February 2013 slide in the southeast corner of the pit damaged the copper recovery pipeline and forced suspension of those operations. More broadly, the slides demonstrated that the pit walls remained actively unstable, excavated geometry, optimized for mining, not for long-term containment. The Montana Bureau of Mines and Geology, which had conducted boat-based sampling and profiling of the pit lake since the 1980s, was forced to suspend direct access due to safety concerns. Between 2013 and 2015, no water column samples were collected. Only in 2017, with the deployment of a remotely operated drone boat, did systematic profiling resume. The critical water level constraint established by the EPA's 1994 Record of Decision and codified in the 2002 Consent Decree defined the ultimate boundary condition for pit management. The elevation of 5,410 feet above mean sea level, approximately 50 feet below the height of the alluvial water table adjacent to the pit, represented the threshold above which contaminated pit water might migrate through the bedrock or alluvial aquifers to discharge into Silver Bow Creek. The consent decree established 14 points of compliance, 7 underground mine shafts, and 7 bedrock monitoring wells whose water levels must be maintained below this critical elevation. As long as the pit remained the lowest point in the groundwater system, contaminated water would flow toward it rather than away. If the pit rose above the critical level, that hydraulic gradient would reverse. The rising water level trend documented since 1984 made clear that without intervention, the critical elevation would eventually be reached. The rate of rise, approximately 0.3 meters per year, meant that the timeline was measured in years, not decades. Some form of water removal would be required to maintain compliance. The question was not whether to pump, but how to manage the removed water. Beginning in September 2019, the pump and treat discharge system became operational. 11:08 p.m. The forensic evidence accumulated over 4 decades of monitoring confirms what the design premise made inevitable. The Berkeley pit is not a closed mine but a permanent contamination management facility, requiring active intervention for as long as sulfide minerals and water coexist within its boundaries. The regulatory documents that now govern the site, the EPA's 1994 Record of Decision, the 2002 Consent Decree, the successive 5-year reviews, codify this reality in legal terms, transforming an engineering failure into an institutional permanent condition. What the physical evidence reveals is not a system that failed unexpectedly, but a system that performed exactly as geochemistry predicted, in the absence of any engineering designed to prevent that performance. The chemical evolution of the pit lake followed trajectories that sulfide oxidation kinetics dictated from the moment pumping ceased. The pH depression, the metal mobilization, the ion cycling, the absence of natural attenuation, each of these outcomes was predictable from first principles and confirmed by site-specific data. The monitoring record maintained by the Montana Bureau of Mines and Geology since the 1980s constitutes one of the most comprehensive long-term datasets on acid mine drainage chemistry ever assembled. Researchers from dozens of institutions and multiple countries have analyzed samples from the pit, contributing to a body of scientific literature that documents the system's behavior in exceptional detail. The Berkeley pit has become, paradoxically, both an environmental disaster and a natural laboratory for understanding the processes that govern contaminated mine water. The forensic attribution of contamination sources confirms the distributed nature of the problem. The pit lake receives input from multiple pathways: groundwater from the flooded underground workings, which drains toward the pit through the interconnected drifts and shafts of the East Camp mine pool, groundwater from the fractured bedrock aquifer, which flows toward the hydraulic sink created by the pit's below water table geometry, shallow groundwater from the alluvial aquifer along the pit's eastern and southern margins, and, historically, surface diversions from the Horseshoe Bend Springs, leach pads, and other contaminated areas. Each source contributes its own chemical signature, but all share the common origin of sulfide mineral oxidation in rock exposed by mining activity. The contamination is not localized to a single point that might be isolated or treated. It is distributed throughout a geological system that extends kilometers in every direction from the pit itself. The wildlife mortality events provide acute evidence of the chronic toxicity that monitoring data document in chemical terms. The deaths of migrating snow geese on the Pit Lake have occurred episodically since the 1990s, with the most severe incident in November-December 2016 killing an estimated 3,000 to 4,000 birds. The geese land on the lake during their southward migration, sometimes remaining for extended periods due to adverse weather conditions. Necropsies of recovered birds revealed internal organs partially corroded by the acidic, metal-laden water, a graphic demonstration of what pH 2.5 and dissolved copper concentrations exceeding 50 milligrams per liter mean in biological terms. The Pit Lake is not merely contaminated by regulatory definitions, it is acutely lethal to vertebrate organisms that contact it for more than brief periods. The microbial ecology of the Pit Lake reveals a system that has adapted to conditions toxic to most life forms. Acidophilic bacteria and archaea thrive in the low pH, high metal environment, occupying ecological niches that exclude competition from organisms requiring more moderate conditions. Researchers at Montana Tech have documented diverse microbial communities, including species capable of oxidizing iron and sulfur compounds at rates that accelerate the very processes generating the pit's acidity. The discovery of water boatmen, aquatic insects of the family Coryxidae swimming in shallow pit water in 2001 demonstrated that even metazoan life can persist at the margins of this extreme environment. More remarkably, researchers have isolated fungal species from the pit that produce secondary metabolites with potential pharmaceutical applications. Berkelic acid, extracted from an extremophilic fungus collected from the pit water, has shown selective activity against ovarian cancer cells in laboratory studies. The same conditions that make the pit lethal to snow geese have selected for organisms producing compounds that may eventually contribute to human medicine. The sediment record at the bottom of the Pit Lake preserves a chemical archive of the system's evolution. Core samples collected and analyzed by multiple research groups show the accumulation of secondary minerals schwattmanite, jarosite, and amorphous iron oxyhydroxides that precipitated from the water column as conditions fluctuated. The massive iron precipitation event triggered by copper recovery destratification deposited over 200 million kilograms of ferric minerals on the lake bottom between 2009 and 2015. This sediment represents iron removed from the water column, but not from the system. Under changed conditions, a drop in pH, the establishment of reducing conditions at the sediment-water interface, some fraction of this material could redissolve, releasing iron and associated trace metals back into solution. The sediment is not a permanent sink, but a conditional reservoir, its stability dependent on the maintenance of chemical conditions that prevent dissolution. The absence of sulfate reduction in the pit sediments, confirmed by multiple investigations, eliminates the primary mechanism by which contaminated lakes can naturally attenuate metal loading. Sulfate-reducing bacteria convert dissolved sulfate to sulfide, which then precipitates dissolved metals as insoluble metal sulfides. This process has been documented in other acid mine drainage systems where it contributes to long-term improvement in water quality. In the Berkeley pit, the concentrations of copper and zinc, both toxic to most sulfate-reducing bacteria at the levels present, apparently prevent the establishment of these populations. The system lacks the biological capacity for self-remediation that might, over geological time, restore it toward natural conditions. Without sulfate reduction, the metals dissolved in the pit water will remain dissolved indefinitely or until removed by engineered treatment. The design ideology that failed at the Berkeley pit was not specific to this site or this era. It was the standard approach to hard rock mining throughout the industrial period: extract the resource, manage operational hazards, and defer closure considerations to an indefinite future. The Butte mines were not designed by negligent engineers or operated by careless managers. They were designed and operated according to the best practices of their time, within regulatory frameworks that assumed continuous operation and permitted treatment and discharge as the standard approach to contaminated water. The failure was not individual but systemic, embedded in an entire apparatus of engineering practice, economic calculation, and regulatory structure that had no category for the permanent consequences of temporary extraction. The regulatory evolution that followed the Berkeley pit's closure reflects the lessons extracted from this and similar failures. The Comprehensive Environmental Response, Compensation and Liability Act of 1980 Superfund created mechanisms for compelling responsible parties to address contaminated sites that the pre-existing regulatory framework had allowed to accumulate. The Berkeley pit's incorporation into the Silver Bow Creek Butte Area Superfund site subjected it to federal oversight and established the legal framework for long-term management. The 2002 consent decree assigned specific responsibilities to the liable parties, Atlantic Richfield Company and Montana Resources, and defined the compliance points and critical water levels that now govern site operations. These instruments represent institutional adaptation to a failure that had already occurred, not prevention of the failure itself. The current state of the Berkeley pit reflects 4 decades of post-closure evolution and 2 decades of active intervention. The water level, which had risen continuously since 1984, has stabilized near 5,323 feet above mean sea level, still below the 5,410-foot critical threshold, but close enough to require continuous monitoring and management. The pump and treat system removes 4 to 5 million gallons per day, treating the water through copper precipitation, lime neutralization, and final polishing before discharge to Silver Bow Creek. The treated effluent meets state and federal water quality standards for aquatic